Hi, welcome all to the online classes. Subject Engineering Physics in BTech Agriculture 4th semester. Topic is light emitting diode, laser. So, on the last lecture, we had completed with optical fiber and we had seen the basic construction of basic building block of optical fiber communication system. There we had seen the source, uh, fiber link, and the receiver. The source are the light emitting diodes and the lasers are the optical fiber sources. So now we are going to study for optical fiber sources. The communication link starts at the point where an electrical signal is converted into optical one. The device doing this conversion is an optical source. Any intense monochromatic source of light in the principle is suitable. However, semiconductor light emitting diode LED and diode lasers are preferred light sources for the following reasons. They give adequate power. Diode laser is monochromatic and coherent source of light. Therefore they can easily be obtained as parallel beam spread over a narrow cone or angle. These are preferred for very long distance transmission. These give adequately low noise. The dimensional characteristics of both diode laser and LED are compatible with those of the optical fiber, which means that coupling of fibers with light sources will be easier. The light from LED or diode laser can be varied or modulated by varying the applied voltage or current through the device, which is essentially the information to be transmitted. So, light emitting diodes are semiconductors PN junction operating under proper forward bias condition and are capable of emitting external spontaneous radiations in the visible range of 370 nm to 770 nm or nanometer. Or the nearby ultraviolet and infrared regions of the electromagnetic spectrum. General structure of LED are special diodes that emit light when connected in circuit. They are frequently used as pilot light in electronic appliance to indicate whether the circuit is closed or not. Now, we try to understand the topics through the mode of slides. Photonic sources of light. Photonic sources of light are those sources of light in which the basic particle of light, the photon, plays a major role. LED and laser. A laser is a device that emits light through a process of optical amplification based on stimulated emission of electromagnetic radiation. The word laser is acronym for light amplification by stimulated emission of radiation. The first laser was built in 1960 by Theodore H. Maiman at Hughes Research Laboratories, based on theoretical work by Charles Hard Townes and Arthur Leonard Shallow. So, the laser stand for the acronym or the full abbreviation of laser is light amplification by stimulated emission of radiation. So this is basically the working principle of laser also. So on the definition of the working principle, we had derived or coined the word laser. Now we understand this statement in the future near in the coming slides. Laser is an acronym of light amplification by stimulated emission of radiation. A laser diode emits radiation of a single wavelength or sometimes a narrow band of closely spaced wavelength. It emits light due to stimulated emission. In this, when an incident photon strikes semiconductor atom, the electrons at higher energy level recombine with lower energy level hole. Due to this, two photons are emitted, one incident photon and the other is emitted due to recombination of electrons and hole. So this is the internal physics which takes place for the working principle of laser. LEDs also work on the same principle, but the major difference is the internal architecture. A laser diode is formed from a narrow channels and it acts as waveguide for light. But LEDs is made up of wide channels. Due to its structure, laser diode emits coherent and monochromatic light, single color. The light emitted by laser diode consists of single wavelength, while LED emits light consisting of wide band of wavelength. Thus, the light emitted by LED is incoherent. Construction of laser diode. The laser diode is made up of two layers of semiconductors, that is P type and N type. The laser diode is made up of two layers of semiconductors, that is P type and N type. Similarly, light emitting diode are also a semiconductor PN junction operating under proper forward bias condition and are capable of emitting external spontaneous radiation in the visible range. So there are two layers of semiconductors, that is P type and N type, in the construction of laser diode. The layers of semiconductors are made up of gallium arsenide doped with materials like selenium, aluminum, or silicon. The construction is same as that of LED, except the channels used in laser are narrow to produce a single beam of light. Next, and one more difference in laser diode is that an intrinsic layer of gallium arsenide undoped is also present. This layer is called active layer. The active layer is enclosed by layers of lower refractive index. This act as optical reflectors. These layers along with layer and these layers along with active layer form a waveguide so that light can travel only in single path in a single and fixed direction. The beam of the light is produced in this section. The metal contacts are provided to facilitate biasing. Next, working of laser diode. The laser diode works on the principle that every atom in its excited state can emit photons if electrons at higher energy level are provided with an external source of energy. There are basically three phenomena by which an atom can emit light energy, and that are absorption, spontaneous emission, and stimulated emission. So, first we understand the absorption. In absorption, the electrons at lower energy levels in absorption the electrons at lower energy level jump to a higher energy level, that is from valence band to conduction band, when the electrons are provided with external source of energy. Now there are holes at lower energy level, that is valence band, and electrons at higher energy level, that is conduction band. Now I explain this. If an atom is initially in a lower state, suppose we had already know the energy levels of uh, atoms. If an atom is initially in lower state 1, it can rise to the higher state by absorbing a quantum of radiation, photon of frequency nu. In laser, the lasing medium can be gas, a liquid, an insulating crystal, solid state, or a semiconductor. For optical fiber system, the laser sources used almost exclusive are semiconductor laser diodes, and yes, photon of frequency nu given by nu equals to h nu, E2 minus E1 by n, where E1 and E2 are the energies of the atom in the state 1 and 2 respectively. This process is known as observation of radiation. The probable rate of occurrence of absorption transition 1 to 2 depends on the properties of states 1 and 2 and is proportional to energy density of the radiation of frequency incident on the atom. Now, next, spontaneous emission. Spontaneous emission, now if the electron in higher energy level are unstable, then they will tend to move to the lower energy level in order to achieve stability. So what do you mean by the spontaneous emission? Uh, Let us now consider an atom initially in the higher excited state 2, that is, by the absorption of energy, it reaches to the second level. Now, we just consider initially the atom in excited state. Excited state with higher energy is inherently unstable. Hence, atom is excited in excited state does not stay for longer time, and it jumps to the lower energy state or energy level 1, emitting a photon of frequency nu. This is spontaneous emission of radiation. If there is an assembly of atoms, the radiation emitted spontaneously by each atom has random direction and a random phase and is therefore incoherent from one atom to another. The probability of a spontaneous emission from second to first is determined by only by the properties of state second and first. So this is denoted by a subscript 21 in some of the standard books, and which is known as Einstein's coefficient of spontaneous emission of radiation. In this case, the probability of spontaneous emission is independent of it. So the energy release will be in the form of light, and thus photons will emit it. This process is called spontaneous emission. Stimulated emission. Now, stimulated emission. In stimulated emission, the photons strike electron at higher energy level, and these photons are supplied from an external light energy source. When these photons strike the electrons gain energy, and they recombine with holes and release an extra photon. Thus, one incident photon stimulates another photon to release. Thus, this process is called stimulated emission. So, according to Einstein, an atom in excited state, energy state, may under the influence of electromagnetic field of a photon of frequency nu incident upon it jumps to a lower energy state, emitting an additional photon of same frequency. Hence, two photons, one original and the other emitted, move together. This is stimulated or induced emission of radiation. This is known as the stimulation or stimulated emission. That means by the energy or by the induction of one photon, another photon is also give the same energy and move together. The direction of propagation, phase, energy, and state of polarization of emitted photon is exactly same as that of incident stimulating photon. So the result is an enhanced beam of coherent light. The probability of stimulated emission transition from second to first is proportional to the energy density of the stimulating radiation, and is given by B subscript 21 U, where B21 is the Einstein coefficient of stimulated emission of radiation. Now the total probability for an atom in state 2 to drop to the lower state 1 is therefore probability from second to 1 is equals to addition of both the Einstein coefficients A21 plus B21. Now the difference between the spontaneous and stimulated emission process. In case of spontaneous emission, the atom emits an electromagnetic wave which has no definite phase or directional relation with the emitted by another atom. In case of stimulated emission, since the process is forced by the incident electromagnetic wave, the emitted light by the atom is in phase with that of the incident electromagnetic wave. The emitted wave is also in the same direction as that of incident wave. So, does one incident photon stimulate another photon to release? Thus, this process is known as stimulated emission. I hope this working principle is clear to all of you. Now, population inversion. Population inversion, the density of electrons at energy level is the population of electrons, and it is more in valence band or lower energy band and less in conduction band or higher energy level. If the population of electrons increases at higher energy level or the lifetime of higher energy state is long, then stimulated emission will increase. This increase of population at higher energy level is termed as population inversion, and this is the requisite state of laser diode. More the population inversion, more will be the electrons at higher and metastable state, and more will be the stimulated emission. Exactly, the population inversion is a very important and basic phenomena required for a coherent source. The photons emitted are in the same phase with the incident photons, and these photons travel as a single beam of light and thus produce coherence. So, for laser action, that is lasing to take place, there should be more electrons at higher energy conduction band than at the lower energy valence band. This situation is called population inversion, because normally the valence band is much more heavily populated than the conduction band. To create this population inversion, high energy forward current is passed through the small active area. Population inversion is necessary condition to create lasing effect, because the greater the number of excited electrons, the greater the number of stimulated photons that can be radiated, and hence the higher emission intensity. In other words, the number of excited electrons determine the gain of a semiconductor diode. On the other hand, a laser diode introduces some two loss. Two main loss mechanisms are: many photons are absorbed within the semiconductor material before they can escape to create radiation. This is the major loss, or the first loss. Mirrors do not reflect 100% of the incident photons. The architectural design of laser, in which there are mirrors which do not reflect 100% of incident photons. This is the second loss. Gain can be increased by increasing the forward current. The forward current at which gain becomes equal to losses is known as threshold current, and the situation is called as threshold condition. So what is there is one situation comes in laser when the forward current at which the gain becomes equal to loss, then it is known as threshold current, and the situation is called threshold condition. At this threshold condition, a semiconductor diode starts to act like a laser. If we continue to increase the forward current, the gain, the number of emitted stimulated photons continue to increase, which means the intensity of the output light also continue to increase. However, we can conclude that a semiconductor diode function like a laser where gain is greater than loss if the following conditions are met: population inversion, stimulated emission, and positive feedback. Now, this is all about the phenomena or the working step of laser. Now, next, major categories of laser diode. There are two major categories of laser diode, that is injection laser diode and optically pumped semiconductor laser diodes. The first is injection laser diode. The operation is similar to LED, except that LEDs are formed by white channels of semiconductor. While laser diodes are formed from narrow channels. We have already discussed this in the construction of laser diode. In this, the light beam travels in the waveguide and the diode itself acts as waveguide. The light beam is amplified by repeated stimulated emission. Second is optically pumped semiconductor laser. In optically pumped laser, the injection laser diode act as an external pump. The third and fifth group semiconductor material act as the bases, and the amplification is achieved by stimulated emission. It offers several advantages such as prevention from interference caused due to the electrode structure. Besides, it also provides an advantage of wavelength selection. When laser is operating in the steady state, the important explanation, when laser is operating in the steady state, and we know the steady state is the state where almost the gain is constant, the gain must equal to the loss. In addition to the stimulated absorption, which is incorporated into the gain coefficient, there are other losses that include absorption at the mirrors on the ends, absorption in the optical cavity for other than the lasing transition, scattering losses at inhomogeneities in the cavity, diffraction at the mirrors, and light emitted out of the cavity. All but the last loss mechanisms are lumped together and represented by an absorption coefficient alpha, which can be calculated out by some mathematical relationship. The transmission losses are accounted for by the reflection coefficient at each end. For a first approximation, one can say that below threshold, the injected electrons create light by spontaneous emission and build up the population inversion. Above threshold, they generate laser light. This illustrated in the future slides. A laser diode is more efficient light emitter than an LED. And the main components of a laser requires three basic components for operation. These are energy source that will raise the system to an excited level or excited state, active medium, which when excited achieve population inversion. The active medium may be a solid, liquid, or gas, and it may be one of the thousands of materials that have been found to laser. Optical resonator, it is essential, consists of two mirrors facing each other. The active medium is enclosed by this cavity. One of the mirror is fully reflective while other mirror is partially transparent. The optical cavity is made used to make stimulated emission possible in more number of atoms in the active medium. This naturally increases the intensity of the laser beam. Next, laser diode Li characteristic. The light energy increases with increase in laser current, but it is dependent on temperature. It is evident from the curve that the light energy increases after a particular threshold laser current. This threshold value of laser current increases exponentially with the temperature. Thus, at higher temperature, the threshold value of laser current up to which the light energy is generated also increases. Thus, it is necessary to operate the laser diode up to threshold value of laser current, because above this value there is no light energy. In order to have a reliable operation, it is necessary to determine the threshold value of the laser current. Advantages of laser diode: low power consumption device, economical, as its cost of manufacturing and operation is low. It can be operated for a long time, portable due to its small size and internal architecture, highly reliable and highly efficient. Disadvantage of laser diode: there are two. They are temperature dependent, thus its operation is affected by a change in operating temperature. It is not suitable for high power application. These are the some applications of a laser diode. Fiber optical communication system, mainly in the fiber optical communication system, the laser is widely used. Barcode readers, you had seen that there is a very high use of barcode readers in big malls, shopping arcades, where at the time of billing they just put barcode reader on a particular item which you purchase, and the details are catch up by that barcode reader, and the light which falls to read out the barcode is laser light. Laser printing and laser scanning, range finders. This is the military application, or in the range finders. Basically, by the name itself, define that you are finding some range, how far that is. So we use the laser as the source, or as the application of laser diode is mostly used in range finders. In medical field, in surgical instruments, in CD players and DVD recorders, there are some of the significant application of the laser diode. Amongst all of these applications, the most crucial realm in which laser diode finds its application is optical fiber communication system. So it is most widely used in optical fiber communication system. Now, light emitting diode, LED. What is an LED? Light emitting diode, semiconductor, has polarity. So light emitting diode is a semiconductor, has a polarity. Normally the LEDs, or the glowing lights, some of the time which are used to indicate for various color codes or for various color reflections, we use LEDs in various projects. So this is a pictorial representation of LED. I hope that everyone had seen the LED in their day-to-day life. How the LED works: when current flows across a diode. Now just see the pictures. When current flows across a diode, basically LED is a semiconductor diode, a PN junction diode. Negative electrons move one way and positive holes move the other way. So the holes exist at lower energy level than the free electrons. Therefore, when a free electron falls, it loses energy. or we can say that the recombination. Then it loses energy. This energy is emitted in a form of photon, which cause light. The color of the light is determined by the fall of the electron and hence energy level of the photon. So this is how the LED works. Calculation of wavelength emitted by LED, where E is the energy, H is the Planck's constant, and C is the velocity of light, lambda is the wavelength of the light. So this is the formula of energy which is given by the scientist, E equals to SC by lambda. Rearranging the term, we finally get the equation lambda equals to H is the Planck constant, C is the velocity of a light, and when you just do the calculation, finally you get the wavelength in micrometer is equals to 1.240 upon energy in electron volt. So this formula is widely used for calculating the wavelength of the light. Inside a light emitting diode, and you see there is a two terminals and one green colored base is lying on one terminal. So this is a diode. So transparent plastic case, terminal pins, and the diode. These are the kinds of LEDs. Now laser, principle of laser diode, or light amplification by stimulated emission of radiation. Now stimulated emission. Now just understand what do you mean by the stimulated emission through the pictorial representation. We had already discussed that three stages are going to be occur in the laser or inside the laser. First is absorption, second is spontaneous emission, and third is the stimulated emission. And between B and C, that is spontaneous and stimulated, there is one more level called population inversion, which we had already discussed. In stimulated emission, an incoming photon with energy h nu stimulates the emission process by including electrons or by inducing electrons in E2 to transit down to E1. While moving down to E1, photon of same energy h nu will be emitted, resulting in second photons coming out of the system. Photons are amplified, one incoming photon resulting in two. This is how the amplification is done. Kindly observe a photon of energy h nu is striking on an atom in the first figure, that is the absorption. That energy is being observed by an atom, uh, and it jumps to the energy state second by consuming that energy. Okay. Now, energy state second, when the any atom reaches to the energy state second, the energy state second is almost unstable state, So for no longer period, the atom will can sustain itself in E2 state and try to come back to the E1 state. So when he is coming, or it is coming back to the E1 state, simultaneously one more photons are continuously incident. A light source is continuously incident. So one photon of a light is moving from the external source. So as the photon or the atom which is moving from E2 to E1 releasing the a photon of light of same energy, that is h nu, get up multiplied or add up with the coming photon, and in this way this is the process for the single atom. Thousands of atoms or millions of atoms are present over there. So the photon or the energy get doubleize, almost doubleize. So this is called stimulated emission. Next, population inversion. Non-equilibrium distribution of atoms among various energy level atomic system to induce more atoms in E2, that is to create population inversion. A large amount of energy is required to excite atoms to E2. The excitation process of atom, so N2 is greater than N1, is called pumping. It is difficult to attain pumping when using two-level system, required three-level system instead. Principle of laser. In actual case, excite atoms from E1 to E3. Now here we, to get the population inversion, we create one more state, that is metastable state. So exciting atoms from E1 to E3, optical pumping. Atoms from E3 decays rapidly to E2, emitting H nu 3. If E2 is a long-lived state, atoms from E2 will not decay to E1 rapidly. Condition where there are a lot of atoms in E2, population inversion achieved, that is between E2 and E1. Okay. Coherent photons production. When one atom in E2 decays spontaneously, a random photon resulted which will induce stimulated photon from the neighboring atom. The photons from the neighboring atoms will stimulate their neighbors and form avalanche of photons. Large collection of coherent photons resulted. Laser diode principle. Consider a p-n junction. In order to design a laser diode, the p-n junction must be heavily doped. In other words, the p and n materials must be degenerately doped. By generated doping, the Fermi level of the n side will n side will lies in the conduction band, whereas the Fermi level in the p region will lie in the valence band. Diode laser operation. This is the pictorial representation of diode laser operation. In figure A, the p-n junction must be degenerately doped. Fermi level in valence band P and conduction band N. No bias, built-in potential EV0 barrier to the stop electron and holes movement. Forward bias EV greater than EG, built-in potential diminished to zero. Electrons and holes can diffuse to the space charge. layer. Application of forward bias. Suppose that degenerated doped PN junction is forward biased by the voltage generator, then band gap EV is greater than EG. The separation between EFN and EFP is now the applied potential energy. The applied voltage diminished the built-in potential barrier EV naught to almost zero. Electrons can now flow to the P side. Holes can now flow to the N side. Population inversion in diode laser or laser diode. So this is the population inversion phenomena by figure. Population inversion in diodes. Just look the figure carefully. This is the energy gap. More electrons in the conduction band near EC, electrons in the conduction band, holes in the valence band. There is therefore a population inversion between the energies near EC and EV around the junction. This only achieved when degenerated doped PN junction is forward biased with energy greater than energy gap. The lasing action, the population inversion layer, the population inversion region is a layer along the junction, also called inversion layer or active region. Now consider a photon with E equals to Eg. Obviously, this photon cannot excite electrons from EV since there is no electrons there. However, the photon can stimulate electron to fall from conduction band to valence band. However, the photon can stimulate electron to fall down to conduction band to valence band. Therefore, the incoming photons stimulate emission than absorption. The active region is then said to have optical gain since the incoming photon has the ability to cause emission rather than being absorbed. Pumping mechanism in laser diode. It is obvious that population inversion between energy near EC and those near EV occurs by injection of large charge carriers across the junction by forward biasing the junction. Therefore, the pumping mechanism is forward diode current injection pumping. For successful lasing action, optical gain, not absorbed, must be high, achieved by the population inversion. So the optical gain is achieved, optical feedback achieved by device configuration needed to increase the total optical amplification by making photon pass through the gain region multiple times. Insert two mirrors at each end of laser. This is termed an oscillator cavity or Fabry-Perot cavity. Mirrors are partly transmitted and partly reflected. Reflection of photons back and forth, higher gain. Fabry-Perot cavity. It's a device to generate the laser action. The photon vibrates to and forth with resonant wavelength. Difference between laser and LED. Lasers are monochromatic, single color wavelength, collimated, non-divergent, and coherent wavelength in phase. LEDs are neither coherent nor collimated and generate a broader band of wavelengths. The peak output power is measured in watt. The peak output power is measured in milliwatt. Graph between optical power and diode current. This is the graph between optical power and diode current. What is laser? Laser we had already defined that light amplification by stimulated emission of radiation. A device which produces a coherent beam of optical radiation by stimulating electronic, ionic, or molecular transition to higher energy levels. When they return to lower energy levels by stimulated emission, they emit energy. Properties of laser: monochromatic, coherent, directional, we had already discussed. Concrete in narrow range of wavelengths, one specific color. Basic concepts of laser: these are the four basic stages of working a laser. Laser construction: a pump source, a gain medium or laser medium, mirrors forming an optical resonator. Pump source provides an energy to the laser system. Examples: electrical discharge, flash lamps, arc lamps, and chemical reactions. The type of pump source used depend on the gain medium. A helium neon laser uses an electrical discharge in the helium neon gas mixture. Excimer lasers use a chemical reaction. So the pump source use depends on gain medium. Now, gain medium, major determining factor of the wavelength of operation of the laser, excited by the pump source to produce a population inversion, where spontaneous and stimulated emission of photons takes place. Example: solid, liquid, gas, and semiconductor. Optical resonator: two parallel mirrors placed around the gain medium. Light is reflected by the mirrors back into the medium and is amplified. The design and the alignment of the mirrors with respect to the medium is crucial. Spinning mirrors, modulators, filters, and absorbers may be added to produce a variety of effects on laser output. This is the laser construction for ND-YAG solid state laser. Highly reflective mirrors, partially reflective mirrors. One is at the partial and one is highly reflective. Flash lamp, pump source, and this is the optical resonator. So this is the one example of laser construction. Laser types according to the active material: solid state, liquid, gas, excimer, or semiconductor lasers. According to the wavelength, according to the active material, we decide the lasers according to two types. One is on the basis of active material, one is on the basis of wavelength. Infrared, visible, ultraviolet, or X-rays. Solid state laser, example ruby laser is a solid state laser. Operational wavelength is 694.3 nm. Three level system: absorb, green, oblique, blue. Gain medium: crystal of aluminum oxide, where small part of atoms of aluminum is replaced with Cr3 plus ions. Pump source: flash lamp. The ends of ruby rod serves as the laser mirrors. Liquid laser, example dye laser. Gain medium: complex organic dyes such as rhodamine 6G in liquid solution or suspension. Pump source: the lasers or flash lamp can be used for wide range of wavelength, as the tuning range of the laser depends on the exact dye used. Suitable for tunable lasers. Dye laser, this is the schematic diagram of dye laser. A dye laser can be considered to be basically a four level system. The energy absorbed by the dye creates a population inversion, moving the electrons into an excited state. Gas laser, example helium neon laser. Helium neon laser, operation wavelength 632.8 nm. Pump source: electrical discharge. Gain medium ratio 5:1, mixture of helium and neon gases. This is the gas laser. Application of laser in scientific purposes: spectroscopy, lunar laser ranging, photochemistry, laser cooling, nuclear fusion. In military, death ray, defensive application, strategic defense initiative, laser sight, illuminator, range finder, target designator. In medical, eye surgery, cosmetic surgery. In industry and commercial, cutting, welding, marking. CD player and DVD player, laser printers, laser pointers, photolithography, laser light display. Now the quiz time or the questions. Which of the following is a unique property of laser? Coherence is the unique property of laser. Which of the following is an example of optical pumping? So, which is the example of optical pumping? Ruby laser. When laser light is focused on a particular area for a long time, then that particular area alone will be heated. Yes, true or false? True. Calculate the wavelength of radiation emitted by LED made up of semiconducting material with band gap energy. Put the values. Uh, wavelength is equals to, we had calculated the formula. There you need to put the value where the Planck constant and the velocity of light is calculated, and the energy, band gap energy is given 2.8 electron volt. Directly put the energy, band gap energy data in that formula. You will get the wavelength, and that come out to be 4430.8 Armstrong. Calculate the number of photons from green light of mercury required to do 1 joule of work. Apply the formula, get the result. Which of the following can be used for generation of laser pulse? ND-YAG laser. What is the need to achieve population inversion to excite most of the atoms? Laser is called as non-material knife. True. DVD uses the laser. True. Which of the following is used in atomic clocks? Measure. Before laser, measures were used, and in atomic clock, measures were used. What is the principle of fiber optical communication? Total internal reflection. What is the other name of maximum external incident angle? Waveguide acceptance angle. A single mode fiber has low intermodal dispersion that multimode. This is true. So thank you. That's all for today. In next lecture, in next lecture, we are going to start with the next topic in continuation to the laser. Thank you.